Hey guys, welcome back to day 26. We're talking about free energy or delta G and non-standard conditions. So let's recap real quick. Delta G is the maximum amount of energy available to do work. Right? And this, of course, is the theoretical limit for a reversible reaction. This leads us to our first problem. All real reactions are irreversible reactions and do not achieve the theoretical limit of available energy. Well, that's fun. Right, that's the second law of thermodynamics in a nutshell. We're just not going to reach the theoretical limit. So let's talk about delta G, standard of a reaction. That value, this value for whatever reaction is occurring, so the reaction is occurring at 25 degrees Celsius, 1 atmospheric pressure, ATM, 1 molar of the solution. What happens if the reaction is not at standard conditions? For example, on standard conditions, 25 degrees Celsius, any reaction that's calculated in like human body temperature is at 37 degrees Celsius. So 25 versus 37, that's a big temperature difference. And so we need to know new values. So we can't just use standard conditions. So let's do an example. Again, we'll start with a simple example. H2O liquid going to H2O gas. The standard free energy change for this reaction is plus 8.59 kilojoules per mole. So we know and see that it takes energy to vaporize water. So we have to put energy into this system. So if you spill water, right, we know heating water helps make it evaporate. However, or yet, water evaporates at room temperature. Even though delta G standard is positive. So this means this is going to say non-spontaneous. However, the process is spontaneous, and that leads us to the question of why. So we know delta G standard for the reaction. All right, and then this does not change It's at 25 degrees Celsius, 1 molar, 1 atmosphere. However, delta G for the reaction can change. Right, due to the conditions. Well, we need the conditions. What are the conditions? Well, of course, it starts with the gas constant R, the temperature T, times the natural log of Q. And Q is the reaction quotient. So Q is, right, concentration of products over the concentration of reactants. R, of course, is 8.3145 joules per Kelvin mole. And so this is how the delta G in blue here can change based on the conditions, even though delta G in black with the degree sign is fixed. Right? That's a very distinctive point. So reactions can become spontaneous because the conditions make them so. So we know that water, liquid water, can go to a gas because the conditions change. And the more heat we add to the liquid water, the more easily it evaporates. And the less water there is in the air, the more easily it evaporates. Where I live, a lot of water in the air. A lot of water in the air. So now, mainly, I say mainly, a lot of times at 25 degrees Celsius, let's say the pressure of H2O happens to be 0.0313 atmospheres. Let's just say that's what it is. So H2O, liquid, going to H2, I must need a new battery in my pen. H2O gas, Q would equal the pressure of H2O gas all over 1, because we don't write the liquid. So that means delta G of this reaction would be equal to 8.59 kilojoules per mole plus 8.3145 joules per Kelvin mole, 298 Kelvin, times the natural log of 0.0313 atmospheres. That gives us a delta G of the reaction to be equals 0, about 0. How do I get that? Well, you have 3 sig figs here, so 8, let me use the blue, 8.59 kilojoules per mole, plus, if you do this math, and technically 298.15 Kelvin is what you get 8590 to 3 sig figs. Negative 8590 joules per mole. So technically speaking, you get about 0 for delta G here. The point of this is that when delta G is 0, we are at equilibrium. And on less humid days, water evaporates quickly, or more quickly. And on more humid days. Water evaporates more slowly. And the question, if you ask why, it's the conditions. So the conditions can determine if water evaporates or not. Where I live, a lot of times in the summertime, it's humid, especially in the morning or at night, and running, your sweat does not evaporate at all if you sweat. And because it's going to be hot out, like upper 80s, very humid, your sweat doesn't evaporate. When it's cold out, dry, sweat evaporates a lot faster, even though it's cooler, because the pressure in the atmosphere is so much less. Now, this blue here, delta G equals 0. Well, we know at equilibrium, Q equals K, and delta G equals 0. So this is going to get us to equilibrium and free energy. Back to the delta G equals delta G standard plus RT natural log Q. We can substitute Q for K, K there, and delta G is 0. So we get 0 equals delta G standard plus RT natural log K, or delta G for my reaction is equal to negative RT natural log of K. They're opposite signs. We know if K can be, we compare it to 1. So K can either be bigger than 1, right, which means it's product favored, which means delta G standard will be negative, and we will be spontaneous. K can be less than 1, which is reactant favored. And delta G standard will be positive, non-spontaneous. And lastly, K can equal 1, which means we're at equilibrium, right? We're neither one's favored. Delta G standard equals 0, so we're at equilibrium under standard conditions. And in your book, just note all our K values are at 25 degrees Celsius unless told otherwise. So that is delta G and K. The first question I want to do is now problem number 64, where we have methanol liquid going to methanol gas. Find delta G standard for the reaction at 25 degrees Celsius. We need to go back to the appendix and look up delta G standard for methanol. This is carbon, CH3OH. Where would methanol be? I've seen methanol. There's ethanol. There's methanol. I have these three, so right here are my methanols. Now, which one's which? So we have to kind of go back up to the top because it doesn't continue. Delta G is the middle one, so it's delta H, G, and S. So we'll scroll back down to methanol here. There are my negative 166.6 and negative 162.3. I'm just going to write them right here. Delta G, standard of formation. For methanol liquid, it was negative 166.6 kilojoules per mole. And methanol gas was negative 162.3 kilojoules per mole. So for A, find delta G at 25 degrees Celsius. How would I do that? Well, the standard free energies of formation. So for A, delta G, standard of the reaction, will equal the sum, the standard free energy changes of products, minus the sum of the standard free energy changes of the reactants. We know that the products would be negative 162.3 kilojoules per mole, and the reactants is negative 166.6 kilojoules per mole. So delta G of my reaction equals that minus that. Delta G of my reaction is going to be equal to positive 4.3 kilojoules per mole. So there's delta G of my reaction. B. Now we're finding delta G. No degree sign here at 25 degrees Celsius under the following non-standard conditions. So for B, I'm going to get delta G equals delta G standard plus R T ln Q. Now what's Q? My Q expression would equal gas over liquid. We don't write the liquid, it's just the pressure of methanol gas. Over 1. So delta G equals 4.3 kilojoules per mole plus 8.3145 joules per K mole times 298 Kelvin times the natural log for A, or for I here, for I is 150 millimeters of mercury. Ooh. Well, I'm going to put in 150 millimeters of mercury. Now, remember, this is important. Q and K need units of ATM or molarity. So to do that, I'm going to divide by 760 millimeters of Hg is 1 atmosphere. And that will make my units work out. So delta G here for I, delta G would be, I got positive 279 joules per mole, or 0.279 kilojoules per mole, depending if you converted kilojoules to joules or joules to kilojoules. Doesn't matter which one you convert, but we have to convert them. That's I. Now for 2, I put 100 in here for the green number, and 3, I put 10 in for the green number. So for I, delta G's. So for I get negative 725 joules per mole, or negative 0.725 kilojoules per mole. And for the 3 I's, I get negative 6,430 joules per mole, or negative 6.43 kilojoules per mole. For part C, explain why methanol spontaneously evaporates in open air at 25 degrees Celsius when delta G is positive. For standard conditions. Well, it's kind of just like the water example we did for C here. Right? Mainly because the vapor pressure for methanol is low. So methanol evaporates at room temperature because there is an equilibrium between the liquid and the gas phases. The vapor pressure is moderate and so when I say moderate, it's 143 millimeters of mercury. At 25 degrees Celsius. So, a moderate amount of methanol can evaporate and remain in the gas phase, which is consistent with free energy values. Number 70. We got a reaction I2 and chlorine going to 2-iodine monochloride. It gives you Kp at 25 degrees Celsius. Calculate delta G for the reaction at 25 degrees Celsius under the following conditions. Standard conditions. So for A, I have a K. Delta G, standard for the reaction, equals negative RT natural log of K. Okay. Now we could look up delta G equals the sum of the products minus the reactants with the free energy of formation. But I'm given K. Much easier. So delta G of the reaction equals negative 8.3145 joules per Kelvin mole. T, 298 K, because we're at 25 degrees Celsius, times the natural log of 81.9. Delta G, standard of my reaction, will be negative 10.9 kilojoules per mole. For B, what is delta G at equilibrium? Right? Now, this is not delta G standard. This is delta G. So, standard conditions, we got delta G standard. At equilibrium, we're looking for delta G. And delta G for the reaction is 0 at equilibrium. That's fun. C. Now we have pressures. So what's Q going to be here? If we write out Q would be the pressure or concentration of I, in this case ICl, squared over the pressure of I2 times the pressure of Cl2. So that's Q. And the reason we need that is we got to use delta G of the reaction is equal to delta G standard of the reaction plus RT natural log Q. We're looking for delta G of the reaction, and that'll be negative 10.9 kilojoules per mole for delta G standard plus 8.3145 joules per Kelvin mole times our 298 Kelvin times the natural log of Q. And ICl is 2.55 atmosphere, and that's squared. And then I2 was 0.325, and CO2 was 0.221. We do that math for delta G of my reaction. I get 264 joules per mole, or 0.264 kilojoules per mole. And that is where I get number 70. 84. 84 is a big one. Barium carbonate going to barium oxide and carbon dioxide gas. Show that reaction is non-spontaneous under standard conditions by calculating delta G standard. Well, I'm not given anything, so I'm probably going to have to look up the standard free energy of formations. And if we do that for barium carbonate, I get negative 1134.4 kilojoules per mole. Barium oxide, I get negative 520.3 kilojoules per mole. And carbon dioxide gas, I get negative 394.4 kilojoules per mole. Now we're going to do products minus reactants. A here, delta G standard is equal to the sum delta G standard formation of products minus the sum of delta G standard of reactants. Okay, so delta G standard of the reaction is equal to products negative 520.3 kilojoules per mole minus 394.4 kilojoules per mole minus negative 1134.4 that gives me a delta G of reaction. The standard free energy change of the reaction to be, I got 219.7 kilojoules per mole. So that's A. B. If barium carbonate is placed in an evacuated flask, what's the partial pressure of CO2 when the reaction reaches equilibrium? Well, there you go. So we're looking for K. When you find K, we know delta G standard, this is B, is equal to negative RT natural log of K. Or and we're looking for K here. That's what we're looking for. We need K. And so K will equal E to the negative delta G standard all over RT. And that's going to be in your parentheses. So let's write this out. K, our equilibrium constant, is going to be equal to negative 219,700 joules per mole divided by 8.3145 joules per mole K times 298K. And all that is E2. So that gives me a K value of 3.1 times 10 to the negative 39. So there's K. Well, what is my equilibrium constant expression for K? K would be equal to the pressure of CO2 over 1. Well, that means K is equal to the pressure of CO2. Why? What's your reaction? CO2 is the only gas. Solid, they're not involved in the equilibrium constant. So the pressure of CO2 is K at 3.1 times 10 to the negative 39 atmospheres. There we go. C. Can the reaction be made more spontaneous by an increase or decrease in temperature? If so, what temperature is the partial pressure of carbon dioxide 1 atmosphere? Well, that would lead me to believe that the answer is yes. And usually, if we increase temperature, the reaction proceeds in the forward direction. So when we say yes, we can increase temperature. So how do we do that? Well, we know we want the partial pressure of CO2 to be equal to 1.0 atmospheres. Since K equals the pressure of CO2, that means Q has to equal 1.0 atmospheres, or just 1.0. We want Q to be 1. Delta G equals delta G standard plus RT natural log of Q. We know Q needs to be 1. We are now going to look for at what temperature this happens. And if you look at this, I know what delta G standard is for the reaction. I know what R is. I'm looking for T. My question is, what is this T? A couple equations. We're gonna break out some equations here. We know that delta G of a reaction is equal to negative RT natural log of K. And we know that delta G standard of a reaction is equal to delta H standard of the reaction minus T delta S standard of the reaction. We also have delta G of my reaction is equal to delta H of my reaction minus T delta S of the reaction. So we are going to use this way. There's a couple ways to actually do this. This would probably be the easier method. We'll look up for barium. So we got BaCO3 solid going to BaO solid plus CO2 gas. We already know what delta G standard is, but we don't know what delta G is. Well, delta G will be 0. So delta G for the reaction is going to be 0. This is going to be 0. Why can't I just make this 0 and solve? That's a good question. Because if the natural log of 1 is 0, So 0 times T times R is going to be 0. Doesn't matter what it is. We can't solve it that way. So we'll solve it this way. We'll look up delta H values. So delta HF for barium carbonate is negative 1213, or negative 1213.0 kilojoules per mole. For barium oxide, it's negative 548.0 kilojoules per mole, and carbon dioxide is negative 393.5. Our entropy values, our standard entropy values will be 112.1 joules per mole Kelvin, 72.1, and 213.8. So now we just got to do for delta H of the reaction is going to be products minus sum of the formations of products minus the sum of the standard enthalpies. And these are technically standard values. So we are technically using the standard values for this. We're assuming they don't change much. So for delta H standard of our reaction, we're going to be, negative 548.0 kilojoules per mole minus negative 393.5 kilojoules per mole minus negative 1213.0 kilojoules per mole. So my delta H, the reaction, is going to be equal to 271.5 kilojoules per mole. S is going to be calculated the same way. And to save some time here, we're just going to put in the 72.1 joules per mole Kelvin plus 213.8 joules per mole Kelvin minus 112.1 joules per mole Kelvin. That gives me a delta S value is equal to 2. I'm sorry, not 2. Let's try 173.8 joules per mole K. Now, this is also 0.173 kilojoules per mole K. So now we're going to solve delta G equals delta H minus T delta S. And we're going to solve for T. Delta G is going to be 0 equals delta H minus T delta S. That's an S. Therefore, T delta S equals delta H. So my temperature will be delta H over delta S, which is 271.5 kilojoules per mole all over 173.8. I'm sorry. How about 0.1738 kilojoules per mole Kelvin. So that gives me a temperature of about 1562 Kelvin, which is quite warm. So Kelvin's the correct unit. The reaction can be actually made more spontaneous by even raising the temperature further. And the entropy, of course, is positive because we're increasing the number of moles of gas. And this is what we expect. So that, ladies and gentlemen, is free energy and equilibrium. Let me know if you have any questions. We'll see you next time.